Hello, everyone. It's my honor and privilege to introduce Nir Gaist, founder and CTO of Nyotron. Nir is a recognized information security expert and ethical hacker. He started his programming at age 6, so my 5-year-old son has some catching up to do. And he began his studies at Israeli Technion University at age 10, so certainly lots of catching up to do. But he holds significant cybersecurity experience, working in various Israeli departments in Microsoft's Israeli branch. He also wrote cybersecurity curriculum for several higher education institutes, and has a vast experience in network penetration testing, and as well as deep knowledge in security breaches and zero-day threats. He also holds patents for creation of programming language used to map operating system behavior. So if everybody give me a warm welcome for Nir.
Thanks. Hi, everybody. So, serious competition. I mean, are the sandwiches good? Am I compete with steak, good steak, or what is it? So thank you for having me here today. It's a privilege. I'm hoping to introduce you to some very cool ideas in the next 45 minutes. And just in case I'm not going to be enough interesting for you with my presentation, I'm going to also show you some cool demos. I'm going to do some live hacks right from here. So I'm the CTO and founder of Nyotron. We are here with DPP, our partners. So you're always welcome to stop by right there and talk to us. So let's start. My presentation is called "Can Security Be Easy?" Because people and vendors, they tend to complicate security a little bit too much. And I'm going to dedicate my next 45 minutes to prove you that security can actually be pretty easy. So with that introduction, I will save your time talking about myself. I'm just having 20 plus years of security, started Nyotron, and really the most important is that I'm a husband, father, and the owner of this charming white Labrador. So that's Shabi. It's a very common Israeli name. So I moved here about 3 years ago, by the way, so that slight accent of mine is Israeli. So rocket science is not easy. I mean, that's why there are just, a few companies that actually develop rockets and launch them to space, because it's not easy. Now let's look at the cybersecurity industry for a moment. That's easy. I mean, really, the bar isn't too high, right? So basically, why really is security not that easy for us today? I mean, what really are the challenges? There are plenty of them, but let's look at the very basic one. Eventually, this whole industry that is valued at, I don't know how, every time I'll throw a number, someone will throw a bigger number, is because of this. I mean, there is no way to differentiate between a good application and a bad application. That's it. I mean, when a virus deletes a file and a good application deletes a file, or execute a process, sorry, in this example, it's really the same thing. There's no way to differentiate. So the whole concept, the whole problem can be described in differentiation. So someone, in order to solve the problem, someone came with a really cool idea of let's enumerating everything. Let's enumerate all the badness in the world, which was cool back then, dozens of years ago. But looking retrospectively, there is just a minor problem. It's called infinity. I mean, really the badness is just infinite. I don't know what he thought back then. Maybe it was less infinite then, but basically, bad applications are infinite. That's all. Saying infinity, I actually mean like really, really a lot. That's from AV test, and these numbers refers just to known attacks and file-based attacks. At the end of the day, there are new and cool things like unknown threats and fileless attacks. So these hundreds of millions of threats refers only to these attacks. So let's dive into the numbers a little bit more. Looking 5 years back, just 5 years, we are at the end of 2018, so that refers to 2013 to 2017. There were 1,500 new cybersecurity companies, tons. That's a lot of new companies. And the number of, the dollars, the global spend on these companies is 383 billion. So many new companies, lots of dollars, and at the end of the day, the really interesting number is the cost of damage, with just $2.5 trillion. Ladies and gentlemen, that's 0.8% of global GDP. That's a lot of money. So what's really behind these numbers? Let's break it down a little bit. First of all, the main reason is that cybercrime is easy too. That's really the problem. Or I should say it's too easy. Another reason is a whole new industry called ransomware. $24 million of ransom paid at 2015 and $2 billion at 2017. So that's really rapid growth. And let's look at some really cool examples before we start to solve the problem. A little bit more about the problem. Samsung ransomware is just an example of a really serious ransomware. Lots of you heard about Atlanta just a few months ago. Just in 2018 alone, $2 million, netted $2 million worth of Bitcoin. More than 30 victims, all are mission critical. I heard that Baltimore's 911 got hacked through a new firewall. By the way, the time it took for the attackers to hack that new firewall was 4 hours only. That's amazing. Really, the guys on the other side are really creative and really cool. So a word about Atlanta specifically happened on March 22nd. The story is very simple. 5 city departments were attacked. Their judicial system, police department, whatever. You read about these things in the news. Can you really imagine how a city looked like when it's under attack? It's really impressive. People can't pay their water bills. They're really disappointed. It's really difficult. The efficacy of the whole system is dropping. Policemen cannot take reports. Really a whole mess. They spent $17 million on recovery. That's all the expense efforts, all the extra staffing, the consultancy. When I gave this presentation last time, it was just a month ago, that number was 5 million or 3 million, so I predicted about 10 million. I was wrong, it was 17 million. The really funny thing is, and I'm sorry to say funny, is that the original ransom demand was 50K. But that gets us to a whole new philosophical discussion. If you do want to pay the ransom, by the way, instead of paying a lot of money, there is a great help desk to ransomware today. Probably much better than most of the security vendors out there. So you should consider it. Last word about the problem before I'm going to talk solutions. I hope that most of you heard about Spectre and Meltdown. The problem is that many people don't. So Spectre and Meltdown, which will lead me to talk about the solution, is just the worst security issue in history. That's really what I think about it. The reason is, and really I think it's really the worst, but still the problem is that people don't talk about it a lot. Someone made really great efforts to keep it silent, but that's still a very big problem. It just allowed the attacker with access to the most sensitive kernel memory, and really everyone is exposed, maybe still exposed, and it affects really all CPUs in the world. That's just how bad is the problem. Now, what's the really big problem about Spectre and Meltdown is just it's not a typical security bug. It's how the CPU works. It's really how it was designed. And what makes it really impossible to protect against it is that it's really something, nothing like any antivirus nor next-gen antivirus ever seen before. Now, having Spectre and Meltdown aside, really the big problem is that it's not the only one out there. Again, we are talking about infinity, right? Remember that problem? So how do you solve infinity? Let's talk about the solutions. After dealing with that amazing idea of enumerating all badness, someone, I don't know, smarter maybe, came with a cooler idea to enumerate less infinity. I mean, it's infinity, you can enumerate more of that and less of that. I'm specifically talking about AI and machine learning. That's a really cute idea. I mean, with putting aside all the fancy words, it's really simple to explain. If you see enough cats, you will be able to identify another cat, right? That's really how the human brain works. My analogy refers to known threats. Let's say all these cats are known, and down there without a name, it's a variant of another known attack. And what's the loophole here? No matter how many cats we will see, we won't be able to identify a big, scary bear, which is pretty threatening too. So unknown remains unknown. That's the conclusion. And please remember that past performance is not an indication of future results. That's more or less the lesson here. So how the utopia look like? How the utopian security looks like? What are we really looking for these days? How can we really solve the problem, if at all that's even possible? So what I expect from a real solution is, first of all, not to be based on learning. Because, as we learned, past is not really an indication. Baselining is the same thing, basically, because some solutions are based on learning your environment, creates a baseline, and then look for deviations from there. The problem is that something can be already in. It must be threat agnostic, meaning that we cannot rely on any past indicators, any past performance. It must be application agnostic too, because applications are infinite. Not only the bad ones, but also the good ones. User behavior is also changing a lot. It's infinite too. And it must be deterministic, meaning it must detect threats, not maybe threats. The whole issue of false positive and performance is something that you know very well. I know it's a lot to ask. That's why I called it Utopian Security. But hey, here's an idea. We did something for dozens of years that didn't work. For sure. I mean, bad is infinite, whether if we try to map it by name or by behavior or by machine learning and AI, whatever. It's just infinite, and unknown remains unknown. So how about doing the complete opposite? It worked for some people in the past. How about trying to do the complete opposite in cybersecurity? By saying the opposite, I mean let's focus on the good instead of bad, and let's not just focus on all the good, but on the finite good. There is some finite to map out there. So what do I actually mean by the finite good and doing the complete opposite? First of all, I literally mean the opposite. What we did all these years is called negative security. What I suggest is positive security. Not application whitelisting, because applications, again, whether they're good or bad, are infinite. I'm talking about a lower level of behavior. There is one application that all of us are using, and the behavior, the good behavior of one application is actually finite. I'm talking about the operating system. The good behavior of the operating system is finite. Someone wrote the code out there, and that code was meant to work in some way, and it's finite. Not the malicious use of that code, not the exploits, but the actual use, the code that the developer meant to write. Let's elaborate about this philosophy more a little bit. Okay, any cybersecurity attack can be described in just 4 layers. I know that people, again, try to complicate. Some will say it's 7 layers, maybe because of other models, but basically 4 layers should be enough. The methodology of the attack, the way the attacker got in, he uses that. It might be a technological vulnerability, it might be a human vulnerability. The attacker is using that to inject some malicious code that will infect the machine and eventually cause damage. The ways to hack into a machine are infinite. Again, vulnerabilities are infinite. Organizational changes are infinite. Applications are infinite. So the ways to get into a point where I can execute a process or delete a file are infinite. But those things that are harmful, that I will try to do at the end of the day, are actually finite. The ways to cause damage to a machine are actually finite. I might want to delete data, manipulate it, send data, receive it, whatever. I'm not saying it's a short list, but it's actually finite. Now tie it with positive security and what I just said. If we'll find one application that should always act the same way and we are all using it, you can actually get a good finite, okay? I'll give you a more practical example, just because we try to simplify things here. There are infinite ways to hack my computer, okay? But at the end of the day, what the attacker might want to do is to delete a file. Okay, here I have a file. Again, the ways to delete that file illegitimately are infinite. But how can I delete that file legitimately? I can give you just a few examples. I can take my mouse, I can point to that file, right-click it, I'll get a context menu, I'll choose delete, that's how most people will do it, and the file will get deleted. Depends on my settings, I might be asked if I'm sure or not. Okay, that's one legitimate way of deleting a file. How Microsoft meant that I will delete a file. There are tons of others. But the truth is that they can be mapped. It looks like 3 steps to you, moving the mouse, point on a file, right-click it. But down there at the operating system, thousands of system calls happened. The movement of the mouse, the file I chose, the right-click, the menu, the fonts to show on that menu. Now imagine that instead of trying to map all badness in the world, I'll map these things. They are finite. What you'll get is a threat-agnostic defense security. That just summarizes what I said. Now let's get back to the basic challenge in cybersecurity. The differentiation, okay? We have 2 processes here. One is bad, one is good, that they try to execute another process. Of course, there is no difference between these 2 process creations. They are completely the same thing. That's why someone tried to enumerate all the bad. But if we look down there to the operating system level, there is a tons of difference. Tons of system calls, okay? Now, let's not go over through all that system calls. I'm not even sure you can see what's going on there. But there are thousands of them. And if we will go up the chain of those system calls, we'll find a lot of differences between good and bad. So I call them indicators of integrity. Sorry, I just had to come up with another term that will be the opposite of indicators of attacks and indicators of compromise. So indicators of integrity, okay? The complete opposite. What you're looking at here are just the system calls that happened at the OS level when we executed a process legitimately. Again, every technical guy that you will talk to will tell you, process execution is process execution, there is no difference. But I'll tell you the secret. There is never, ever just a process execution. Things will always happen before, not after, before, maybe also after, but we want to prevent that process creation, so we better look before, unless it's malicious. Only if that's a malicious process execution, there is a slight chance that's going to be just process execution. But if it's legitimate, there will be tons of thousands of other system calls that will occur before a legitimate one. Can you get me back my presentation? So what you're looking here is just 3 system calls, an example of 3 system calls that will constantly happen when you execute a process legitimately. Now you know what these are? These are the way Windows works when you just take your mouse, choose a process, and right-click on it. Why they happen, those 3 specific system calls? There is a very clear reason. Not always we understand that reason. I doubt that even Microsoft understands the reasons. But there are just constant, very, very constant system calls that always happens. So you can choose a sound to play whenever you do something in Windows. Okay, we can set a sound for email, for errors, for whatever. One of the sounds that you can set is for selecting a file. You don't have to choose a sound file. You don't even have to have a sound card. But the operating system will check if it should play a sound when you do that. So that's what you're looking at here. Those 3 system calls represents that. Now you know how many system calls happens before a legitimate process creation? Approximately 2,700. So there is a lot to map. Back to theory, when you do that, I look at it as creating a GPS for the operating systems. You can't really map all the ways, the weird ways to get from here to San Francisco, okay? You can go through San Diego, that's okay. I mean, you might do that. But that means you are insane. That means I should not trust you, okay? So you better want to know if you have a process that works this way in your organization. Okay? If you will take your Waze or Google Maps, whatever you use, I hate both, you will put the address of Moscone Center, which is a different conference, and it will offer you like 3 reasonable ways. Those are the ways you should take, unless you know better. But none of them will be through San Diego. And that's exactly what positive security means. You can map the legitimate ways to get from any point to a potentially harmful activity. There is really a finite number of ways to get from win key to file deletion, from whatever you want to file creation. And you can map all these things. I don't know about you, but we did it. So there are many other examples, okay? The UAC settings, there are certain ways to change the UAC settings. The operating system will always check what language to show you when you open a dialog. It will always check what is the current setting to show you so you can change it. So by mapping all of these things, you get a way, a legitimate way to do something. So we did it, and at the end of the day, here are some thumb rules, or rule of a thumb, whatever, you know better. Obviously, the more IOIs you will find, the better security you will get. Now imagine that you look for IOIs from different processes. That means the attacker will need to exploit 2 different processes in order to mimic that legitimate behavior. Not to say that attackers are not even trying to mimic legitimate behavior. They're actually trying to do the opposite. They don't want you to see what they do. They don't want you to hear a sound. They want to keep it low and slow, which makes it even easier to detect them using this way. So maybe the most interesting aspect to that is fewer false negatives and false positives at the same time. Because today, when you want to solve a false positive in your product, what you do is creating an exception. That means that you need to choose between true positives and false positives. You need to choose between security and more security and less security. And all your security products has this slider. Okay, choose. You want me to secure you, or you are willing to compromise in order to have less false positives. That's really simple. When you map legitimate behaviors in order to detect the unknown by using IOIs, indicators of integrity, you can actually get more security and less false positive. And as you get more security, you will have less false positive. And that's really unique and really amazing. Because as you add more IOIs to the correlation, the attacker will need to work harder to mimic legitimate behavior, and at the same time, you will eliminate false positives because you are more accurate in your detection. That's amazing, by the way. So I won't bother you more with these That's just an example of how we map legitimate behaviors. We actually doing it using what we call BPM, behavior patterns mapping. That's a whole new programming language we've developed just for mapping legitimate behaviors at the kernel level. So that's how it looks like. That's actually a pseudocode. I'm not going to show the actual language. But to the most entertaining part, a demo, I'm going to use my machine to show you how positive security really look like. And what you really enjoy is live hack. So let me just sorry. Are you all still awake? Thank you. Okay, so what do we have here? We have two virtual machines. We actually have three. The third is the server. You don't care about the server. One is a victim. One is an attacker that doesn't have, he actually had a wallpaper, but for some reasons you can't see it. So we're going to use this machine to attack this machine. Okay, that's really obvious. And we have some next generation stuff installed here, not Nyotron. We also have Nyotron, but there are some AV and next-gen AV installed in here. I'm not going to talk about them, but they are up to date. And all settings are most restrictive. This humble hedgehog, it's a hedgehog, not a porcupine, not a ferret. It's a hedgehog. They are very, very common in Israel. That's okay. That's our product, Paranoid, that operates at the kernel level of this machine. And Paranoid can operate either on detection or prevention, or hybrid. We will start with detection because we want you to enjoy the attacks all the way. But Paranoid is completely based on positive security, meaning that when the actual malicious activity happens, we are already in the right state to block it. So that's what's going to happen. You can actually deploy it completely transparent to the user. We don't have to have that hedgehog, especially when in the United States people don't know that animal. So that's their victim. Now, to the most impressive part of this demo, that's the Paranoid War Room. And the Paranoid War Room is a very unique management system that we've developed after we understood that people love this much more than security itself. That's a multi-touch supported management system. We can show you here any size of network, be it a single node or hundreds of thousands of nodes. You can actually play with that sphere all day long. It won't break. And we will show you the precise location of the attack. And most importantly, is the level of details that you will get, because we detect things based on the actual system calls. So I have more 10 minutes, right? 10 minutes, right? So we better go. So basically, that's the war room, and you will be very interested to see, again, how an alert look like. So let's jump to the actual attack. So we will do two attacks. One is the most common, one is the most cool. We'll start with the most common, which is a ransomware. Okay, so we have here some data that's currently completely fine, as you can see, not encrypted, and we're going to send a very authentic fake LinkedIn invite to our victim from Jimmy Demani, the CTO of Placebo Bank. And no matter where a victim is going to click here, you will get to, again, that's a completely legit fake LinkedIn invite that will get you to a not legit LinkedIn website that will infect you with a ransomware using a drive-by-download attack. So we are sending our victim this invite, and we do have a Metasploit running here in the background with the exploit up and running. Basically, again, there is a web server running in the background with a malicious LinkedIn website. So that's an empty folder. Our pretty cool variant of ransomware of Chimera is going to steal the data, not just encrypt it. So we will see both encryption and exfiltration. That's where our stolen data is going to be displayed. Let's get the email from Jimmy from LinkedIn. Looks good, right? Let's be suspicious because we are very aware and we will view the profile first instead of accepting it. And we got to the fake LinkedIn website. And in a few seconds, we have 72 hours to pay our ransom, 3 Bitcoins, $1,200, which was really cool back then. It's way more than $1,200 today. So if you got attacked with a ransomware back then, I hope you bought some extra Bitcoins. And switch to our, oh, sorry, that's really confusing. The data is here. By the way, the data is here after the encryption because in order to bypass DLP solutions, probably. And looking at the data here, file names are similar, are the same. They didn't change because this ransomware is pretty mean and it's much harder to filter all the infected data if you don't change the file names. And by analyzing this ransomware, we know they did it on purpose. The data is encrypted. Okay, that's a game over. No one will be able to pay his water bill. And let's take a look on what we have detected. So we have orange objects because we are on detection mode. On prevention mode, that would have been red. And we have several ways to look at what happened. We can see all the infected endpoints. We can see all the infected processes. And basically, it works with filters. So now we are looking at this process on this machine. Eventually, we have one machine infected with 2 processes. We can have 20 processes on one machine. We can have 20 machines with one process. That's possible. Now look, if we dive into the attack on that specific machine, we don't see signatures. We see categories of behaviors. And every row in here, it's a detection. Because we use positive security and we've mapped all the ways to write files, to modify files, every file modification here was detected and prevented if we were on prevention mode. So not even a single file. Again, if we were mapped like some antivirus companies out there, if we would have mapped the illegitimate ways of encrypting data, we would probably have some rule look like 10 files in a row too quickly, that's bad, let's prevent the 11th one. But no, here we actually analyzed every encryption, and that's why we would have blocked every single file. And we also detected the illegitimate communication, again, by understanding how communications should be made. So my favorite feature is the storyline. We actually visualize the attack too. And that's actually a player. So if you hit play, you can see a step-by-step. How the client started Internet Explorer that connected to this IP, downloaded this ransomware, executed it, and read, wrote, and didn't override it at the end of the day, the data. That's how, by the way, I know that the ransomware did it on purpose. Because it didn't just deleted the original files, it also it actually override these files. It changed the names of the encrypted files. So eventually communicated back, that's the exfiltration. Let's show you quickly, because I promised you also a cool one, not just the common one, quickly another demo. I have a completely different machine in here. Because I'm not going to do this demo on my machine. It's too cool. So, So in the meantime, when we boot this machine up, and you will see it in a moment, what I'm going to show you is called Rubber Ducky. So some of you might know it. The thing is that most people don't. And the reason is that no one's talking about it. The reason no one is talking about it is because no one can stop it. So it looks like an innocent flash drive, but it's not. Okay, that's actually a keyboard that looks like a flash drive. Does anyone here blocks keyboards in your organization? No. No. You might have device control to block flash drives, but that's not a flash drive. That's a keyboard. It emulates a human interaction device, a keyboard. And what it does, once I plug it in, it immediately starts typing whatever I want. So what I'm going to show you is a Rubber Ducky that has Rubber Crypt. That's how we call that Rubber Ducky-based ransomware. That is fileless. There isn't any file here. That thing will literally type the attack to the machine. So if you have visited our booth at Black Hat, you could have bring your own machine and plug it into your machine and see, that's really cool. And there's nothing you can do about it. Some people did it. They had tons of cool security solutions for their machine, and they were willing to test it. And the version we had there just encrypted one file. So you can see that victim. There are some documents on here, and the same security solutions are installed on that machine, and they are up to date, including whatever. So files are okay. And I'm going to plug this thing in, and I'm gonna let's open the folder and see what happens. And I'm gonna step aside. I'm not gonna do anything. And you see that this cool thing opens our CMD, and you can't see the CMD because it smartly just moved it aside. And it takes a few moments because it literally types the attack to the CMD window. It is a binary file originally, so it literally types that into base64. So it just types that into CMD. It's going to use PowerShell. Here's PowerShell. And you will start see the files in just a few moments. The files will start get encrypted. And at the end of the day, we'll delete all the original files. So what you see here is an unstoppable attack using any of your current solutions. I'm so sorry. And as you can see, we need to pay 13.37 Bitcoins to this one. So that's Rubber Ducky. Positive security works. It works very well. I'm not going to switch back to my presentation because I don't have time. This utopian security I discussed earlier is possible using positive security. I hope you enjoyed the presentation and my demo. I'll be here for another few moments, and my colleague Russ is here too. I'm not sure they actually saw you. Okay. Thank you so much.